Now, in the previous class we have discussed about the probability problems and all. Now, next we have to discuss the properties of mathematical expectations. In the earlier class we have defined what is mathematical expectation. So, mathematical expectation is denoted by E of x and it is given by summation of x into p of x here when x is a discrete random variable. Right? Similarly, when x is a continuous random variable, it is given as integral over x into f of x dx, where the integration is from minus to plus infinity. This is the case when x is a continuous random variable. Right? Then, this is the mean of the random variables. So, mathematically we spell it as expectation of x here. Now, also we have to find the variance for the random variable. So, the variance formula can be expressed in two types. The first one is, it is simply expectation of x square minus expectation of x whole square, right? Also, it can be written as expectation of x minus e of x whole square. So, if you simplify this part by considering x as a variable a and e of x as b, and if you just use the formula a minus b whole square, then you will get the above only, right? So, any one of this formula we can use for variance, that is expectation of x square minus expectation of x whole square and expectation of x minus e of x whole square. So, there is a lot of difference between these two, expectation of x square and expectation of x whole square here. So, here we have to take a square of x and here we have to take a square of entire mean. E of x is nothing but again the mean only here, right? And if we consider that g of x is any function on the variable x here, then expectation of g of x is given by summation of g of x into p of x when x is discrete random variable, and when it is continuous, integral over g of x into f of x dx when it is a continuous random variable. So, here I am using for random variable a simple notation as RV here. The properties on mathematical expectation. Now, you can prove these properties using the discrete random variable and as well as the continuous random variable. Now, if you see the first property here, if x is a random variable, then we have to show that expectation of kx is equal to k into expectation of x, where here k is any constant, right? So, we can prove using the discrete and as well as using continuous. So, here I will prove the problems using continuous random variable, but after that you just prove this using discrete random variable, right? So, here it is clearly given that x is any random variable we can take and expectation of kx equal to k into e of x here. So, by definition here, what is expectation of x? It is integral over x into f of x dx, right? So, if k is any function on that, then expectation of kx is equal to integral over kx into f of x dx, where integral is from minus to plus infinity. So, when k is a constant, we can express it as k into integral x into f of x dx. It is just like that integral over 2x, we are writing it as 2 into integral x here. But we know the condition of probability density function that integral over x f of x dx is nothing but here e of x here. So, k into expectation of x. So, therefore, expectation of kx is equal to k into expectation of x. That is the first property. Now, if you see the second property here, if x is a random variable, then expectation of k plus x is equal to expectation of x plus k, right? So, here again I am considering this as continuous random variable. So, expectation of x is here integral x into f of x dx. So, from minus to plus infinity. So, when I am taking the k plus x is any function on the random variable, so it is integral over k plus x into f of x dx. So, minus to plus infinity. It is nothing but in the form of integral over a plus b. So, just split that integration here, integral k into f of x dx plus integral x into f of x dx. So from minus to plus infinity regarding the limits, right? So here k is constant, we can bring it outside the integral. So k into integral minus to plus infinity f of x dx plus integral x into f of x dx by definition is e of x here. But here integral f of x dx is 1. That is the mentioned in the condition of probability density function, that always the integral over f of x dx equal to 1 for continuous random variable, and for discrete random variable summation x into p of x is equal to 1. So k plus e of x. So therefore expectation of x plus k is equal to k plus expectation of x here. Since integral f of x dx is equal to 1, so this condition you have to mention there. Right? So these are the two properties of that. We have three more properties we will look after. If we consider two constants a and b, right, then expectation of ax plus b is equal to a into expectation of x plus b. That means we are combining the first two properties, right? Then it is clearly mentioned that a and b are two constants, right? Then by definition expectation of x is integral x into f of x dx from minus to plus infinity. So expectation of ax plus b is integral over ax plus b into f of x dx, right? So just like the second property here also we will split into that two integrals. So integral ax into f of x dx plus integral b into f of x dx. But remember here both a and b are two constants, right? So again bring these constants outside the integral. So a into integral x into f of x dx from minus to plus infinity plus b into integral f of x dx from minus to plus infinity. So by definition integral x into f of x dx is e of x. So a into e of x plus b into integral f of x dx will be equal to 1. Since the second condition of probability density function. So therefore expectation of ax plus b is equal to a into expectation of x plus b, right? So these are the three properties on mean expectations.